we're on this slide. Levels of memory hierarchy. Why do we need to have this hierarchy? What's the purpose? Very simple. We want to have unlimited memory space with very high speed. So which level or which levels provide high speed? The upper levels. Which level or levels provide unlimited capacity? The lower levels. Okay? So whenever I want to access something, I hope I can get them from the top levels. And whatever I need will be stored in the lower level. Okay? So hopefully the hit rate to the upper levels will be high enough such that only a few accesses will have to go all the way through to the bottom levels. So what is my average memory access time? The average memory access time will be hit time up level 0 plus miss penalty of, miss rate this should be hit time times miss penalty of top level. Okay? Very easy. So when I have a miss rate and miss penalty of the top level, then what is the miss penalty of the top level? Miss penalty will be the extra time needed if I want to access the information from one level down. So that's the penalty. So if you walk away with something in the supermarket, the fine will be 50 times the list price of their product. That's the fine. Okay? So suppose you walk this away from the supermarket and this is marked for $10. Then how much is the fine? 500. Right? 500. So after you pay the fine of 500, does this belong to you or belong to the supermarket? Still the supermarket. So you want this? 10 more bucks. Okay, so now you understand what penalty means. It's extra. Okay, so the penalty is the extra. So this is a very useful equation, but when it comes with more than 2 levels, then this equation is somewhat recursive. Okay, so I'm not going to give you the detailed equation. You derive that on your own. It's somewhat like a recursive equation. What if I miss again at level 2? What if I miss again at level 3? Okay, next thing I'd like to mention to you is the capacity. Capacity of the register is 100 bytes, kilobytes, perhaps up to megabytes, megabytes perhaps up to gigabytes, gigabytes perhaps up to terabytes. So size comparison of these levels will be like 3 orders bigger, 3 orders bigger, and 3 orders bigger. And last time I told you what the capacity of a tape would be compared with a disk. So the tape capacity is again 100 to 1,000 times larger than the disk. Okay? And this is somewhat random access. And this is sequential access device. A tape has to be sequentially accessed. But for a disk, you have the seek time, you have the access time, you have multiple platters, maybe double-sided on each platter. Okay, and cost-wise, per gigabyte cost would be thousands of US dollars, hundreds of US dollars, $1 US, and perhaps less than, much less than $1 US in year of 2000 or so, about 10 years ago. And could you tell me who uses the registers? CPU, wrong. CPU is super passive. CPU does whatever it's told to do. User? Compiler is the correct answer. Compiler decides which register will be used at when. Okay, when I say when, I mean according to the program instruction order. And what component uses L1 cache? Controls L1 cache? The cache controller. Cache controller is 99 point something % hardware, but it can be software. For instance, maybe in my program, I can dictate some portions to be non-cacheable. Okay, some portions of the cache of my address space, some variables will be non-cacheable. Okay, or OS can decide on that. So 99 point something % hardware decides when and how to use the cache memories. Next is the main memory. Who determines how to use the memory? This is also called main memory or primary memory. What component? Operating system. Operating system is huge. Which part of the operating system? What function?
Memory manager.
Virtual memory manager. Okay, virtual memory manager sees the demand from the processor and determines which pages on the disk should be placed in main memory at where. Okay, which ones and where to place them. That's the virtual memory manager's job. And the disk, who uses the disk? You, the human being. Okay, and also the tape. So you need to mount, unmount disk, put files in, and delete the files that you don't want anymore. Okay, so these are the users of these memory hierarchies. And speed-wise, faster and slower, of course. But when I say fast, what do I mean? When I say fast, what do I mean? Latency? Throughput? Throughput is some kind of speed also. Okay? The throughput of a disk is very high. So whenever you find the beginning point of your file, the transfer rate is huge. Yet for this one byte at a time. And after every access, you need to provide it with another address. Very troublesome. Okay, so 1 byte at a time. And the transfer between here and here is 1 byte at a time, but in the unit of L2 cache line. Every time you need to fill a whole L2 cache line. Every time you need to fill a whole L1 cache line. And depending on the data type of the program, byte, half word, word, and whatever. You have a question?
A cache line, the size of that is dependent on the cache?
The cache line size is, you decide on that. But the hardware, once the hardware is fixed, the line size is fixed. What about the page size? OS decides the page size. Is there only one size for all? Or there could be different sizes? Could be both? Yeah. Fixed size or variable size? Then if it can be both, then it can be variable size. Okay, so the typical page size is from 128 bytes, very small page, to megabyte, very huge page size. When do we need megabyte page size? When do we need that? When we want to render something on the screen. Okay, 4K page size doesn't help much. Whenever we need something, we need like a megabyte of information. So the page size varies. Line size also varies. But basically, these numbers are more fixed, like 32 bytes per line, like 256 bytes per line. It's more fixed. Okay. Next page. Focus on common cases. This is design principle number 3. Okay, so common sense guides computer design. Since that machine is too complicated, so we really don't know how to design the right computer. We only know how to design a good computer. Okay, so since it's engineering, common sense is valuable. When it comes to engineering, we just want to solve the problem. We don't really care if we have the true understanding of the problem and if our solution is optimal. Okay? So for the engineering problems, we just want to make it work and see whose solution is better, cheaper, faster, whatever. In making a design trade-off, favor the frequent case over the infrequent case, that's of course. So, for instance, instruction fetch and decode unit is used for every instruction. It's used more frequently than multiplier, so optimize fetch and decode first. Another example is for database server has 50 disks per processor. Storage dependability dominates system dependability, so optimize it first. And frequent case is often simpler and can be done faster than the infrequent case. It will occur more frequently. What will occur more frequently? Simple things. Okay? Just like when you want to learn Chinese, how many Chinese words are used daily? You know how many? Only 5,400. Okay, used daily. Other than these 5,400, those are very rarely used Chinese words. Even those Chinese-speaking people may not recognize them. Does that make you feel more comfortable? No, still not. Okay, you need to work harder. So for English, how many English? How big is your English vocabulary? A little over 100. You just speak drink, eat, sleep, rest, something like that. So the most frequent cases are used so frequently that 99% of the operations we used constitute only like 7 to 8% of IBM 360 instruction set instructions. Okay, it has a huge instruction set, but only that many instructions are used 90-something% of the time. And the rest are only a few percent of occurrence. Okay, so we don't care if we slow down overflow, since it's a rare case, but overall performance improved by optimizing for the no overflow case. So optimize your design for situations when there's no overflow. Then what is frequent case and how much performance improved by making case fast? That's what Amdahl's law is trying to tell us. So the Amdahl's law says, if this is execution time, original total execution time, and if the green portion is the portion that you intend to improve, then after the improvement, the sizes of the red portions will not change. Only the size of the green portion will shrink. So wherever you want to do improvement, expect to get performance improvement only within that portion. That's what the Amdahl's law says. Okay, the equation is like this. Execution time new is equal to execution time old times the unchanged portion in percentage plus the portion that's going to be changed over the speed of the enhanced portion. Okay, so if this portion constitutes 90% of your old execution time, then your speed up, no matter what you do, even at light speed, your final speed up will be no more than 1.1. Okay, only 1.1. So the overall speed up is the execution time old over execution time new, and plug this equation in to the denominator, then you get this. Okay, that's a very simple equation, but the meaning behind this equation is do improvement to the majority of your execution time, to the majority of where you spend your execution time on. So best you could ever hope to do is this, the maximum speed up. In other words, make the fraction of your enhancement as much as you can. So if we have a new CPU which is 10 times faster than the old CPU, but for an I/O-bound server, only 60% of time, 60% of time is waiting for I/O. So for the rest 40% of your time, if it's 10 times faster, 40% will become 4% if it's 10 times faster. Okay, and your overall execution time will be 64% of the original execution time. So for 10 times faster CPU, your server, I/O-bound server speed up will only be 1.6. So don't spend too much time, too much money on your CPU upgrading. Apparently, it's human nature to be attracted by 10 times faster, versus keeping in perspective, it's just 1.6 times faster. But now let's focus only on the processor itself. Don't worry about I/O anymore. For processor, the time you spend is equal to this equation. This equation says the time your CPU will need is equal to the number of instructions you need to execute, plus times how many cycles you will spend per instruction on average, times the cycle time. How long a cycle will be, how many cycles you will need for an instruction, and how many instructions your program will need to execute. So for a loop, if the loop body runs 10 times, then you have executed 10 times the instructions in the loop. Okay? So you want to improve processor performance. In other words, you want to reduce CPU time. Then you can either reduce this term or reduce this term or reduce this term. How do you speed up cycle time? How do you speed up cycle clock rate? How do you do that? More advanced technology, circuit technology, IC technology, or deeper pipeline. Okay, How do you reduce number of cycles per instruction? Shallower pipeline depth, okay? Or simpler instructions. How do you reduce the number of instructions executed?
Better programming, better compiling.
Use more powerful instructions. Okay, so whenever you want to reduce the number of these terms, the amount of these terms, then these two terms may become larger. Okay, so it's never an easy task to optimize, to improve the processor performance. So let's draw a table using the instruction count, cycles per instruction, and clock rate as the three indices. And these are the factors for improvement. So when I say technology, I mean IC technology. Everything is technology, but here technology refers particularly to IC technology. So IC technology can improve clock rate. Organization, how deep your pipeline will be, how many function units you use, where to place each thing. That can improve your cycles per instruction. Can that improve your instruction count? Maybe not. It has nothing to do with the machine code. Can it improve the clock rate? Maybe. Put the communicating components close to each other. That may increase your clock rate. Okay, making the information communications latency shorter. Instruction set. If you're going to design a completely new CPU, you start with the instruction set architecture. What instructions you want to choose? Okay, and compiler. A good compiler can always compile good program for you. So the instruction count may reduce. And the CPI, maybe, for instance, for a sys computer, I'll choose to use the simpler instructions. I don't use those super weird instructions because super weird instructions may take a lot of cycles to execute. Okay, so compiler will help instruction count and CPI. But for the RISC type processors, every instruction is one cycle long. So maybe for RISC processors, compiler will not help CPI. Has nothing to do with CPI. Okay, that depends on your instruction set architecture. And program, how do you relate this program to compiler? Compiler generates program. Program is generated by compiler. Why do I put another thing called program here? That is if you write your own program. You don't count on the compiler to write the program for you. So being a computer scientist, do you like to have a compiler? Another question, do you like to have an OS? The answer is yes if I'm lazy, but no if I want to do it myself. I can do a better job. Okay? Can program have to do with CPI? Yes or no? Sure. If compiler can do something about this, then my program can do something about that too. Okay. Can compiler help the clock rate? Maybe not. Instruction set, can instruction set help the clock rate? Yes or no? 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 If not, then how come RISC processors usually have much higher higher clock rate? You say yes or no? The answer should be yes. Okay, so this table is only for your reference. You can put an X here. Can you X instruction count for the organization? Maybe not. And here CPI, definitely. Clock rate, definitely. For technology, okay, I agree with the author. Only the clock rate. So if you like, you can X this. And you can also X the CPI for the program. Remember, for the research type work, there is never a standard solution. Okay? All the standard solutions are only for your reference. And you always can come up with a better idea. And any question is welcome. Ask me any question you have. What's a clock cycle? Tell me, what is a clock? This is a clock signal. What is a clock signal? What is the clock signal in nature? How do you define a signal to be a clock or not to be a clock? Okay, the reason we call it a clock is it comes regularly. Okay, the signal comes regularly. You can expect it to come after a predictable time period. Then it comes again. Okay, and again, and again. But other than that, what is a clock signal? You see, you have X input, you have Y input, you have Z input, you have clock input. Is clock input special compared with the others? Or it's nothing but yet another signal? What is the closest relative to the clock signal? Somebody know the answers? Okay, let me draw you a gate. If this is a gate, this is a circuit, an unknown black box. We have X input. Sometimes we have Y input. We have something called enable. Have you heard of enable before? And we have clock. Whoops, some people draw the clock here, and some people wire it to here. So anything special about the clock signal? What is a clock signal? Okay, so clock is just one of the signals, nothing particular. And its closest relative is the enable signal. Do you know enable signal? Enable signal is nothing but an input to the final AND gate. If I don't let you go through, then you cannot go through. If I let you go through, then you can go through. Right? Nothing but an input to the final AND gate. That's the enable signal. What about clock signal? It's nothing but yet another input to the final AND gate. So if you want to call clock and enable, it's okay with me. Nothing but an enable. Okay? Okay, now you understand what clock is. So the clock signal is seen by this and this. This diagram is somewhat misleading. If I were to draw this diagram, what I'll do is this. This is a timing diagram of the clock signal. And let me remind you, this diagram is independent of this diagram. This is the circuit diagram. This is the timing diagram of that clock signal. So when you look at the circuit, don't look at this. Don't look at this at all. If you want me to add the clock signal into this circuit, then I'll put clock here and draw a line, connect it to here, and connect it to here too. Okay, to every latch. So whenever the clock has a rising edge, this thing gets triggered to latch in this information. This thing gets triggered simultaneously to latch in information from here. Okay, so they both take action at the same time, latching in different information. Okay, and for whatever sequential circuit, you always have some circuit to calculate and some circuit to memorize. For a pipeline, the design, then you have combinational latch, combinational latch, combinational latch, combinational latch. Okay, so now you know how to read this diagram. So for the old days, there can be 10 gate delays in the combinational logic. Why? Because of the clock rate. We set the clock rate to megahertz, even to kilohertz in the old days. And we have memory, we have I/O. We think the CPU speed is appropriate if it's 1 megahertz. Okay? For that reason, we need to have a system view. For that reason, we decide CPU should have what kind of speed. And at that speed, it is allowed to have how many gate delays within the combinational circuit. And at that time, most of the delay time occurs in the gates only. Okay, today, we need to speed up our processor clock rate. Why do we need to speed up our processor clock rate? First is, of course, for the performance reason. The second reason is weird. For the marketing reason. Because if I speed up the clock rate, how much do you understand what processor performance means? That translates to how fast I can run which benchmark? Sorry, I don't know what that benchmark is. That translates into how fast it can consume the battery power. That's not what I want. Okay, and I don't understand what joule is, what wattage is. Do you care about how many joules or how many watts? Which one do you care more? Sorry, I don't understand those terms. So what do you understand? Clock rate only. Okay, most people can accept the idea of clock rate. 10 gigahertz is good enough for you? 11 can be better. Okay, so it's easy to sell. So for the marketing reason, people start to increase the clock rate like crazy for no reason. For no reason but one. To have a better sell. Okay, so the pipeline depth increases from 5 to 8 to 10 to 15 to 20 to even up to 30. If you have so deep pipeline, you can imagine how worse, how bad the structural hazard, dependency hazard, and control hazard can become. Okay, so the reasonable pipeline depth is little over 10 or around 10. More than that, it's only for commercial reasons. Mostly for commercial reasons. And only a little for performance reason. Besides, today, most of the latency occur in wires but not in logic gates. Why? Because the circuit becomes huge, the wires become so close to each other, so the coupling capacitance becomes very high. The latency on the wires occupy about 70 to 80 of your clock period. Okay, not only that, the energy or power consumption, 70% of the power is leaked, wasted. Okay, and 70% or even more of the latency is only on wires. Okay. Okay. So we have today, clock rate is determined by numerous time of flight issues like clock propagation, wire length, drivers, etc., plus gate delays. Do you know what clock propagation means? Do you know what problem this will cause? Have you heard of clock skew problem? Clock skew problem. How many of you have heard of clock skew problem before? One? No more? Okay, let me tell you what that is. Suppose I have a big die with circuits on it, right? I have a clock generator. This circuit generates the clock signal. Okay, this clock signal will have to be sent to everywhere on the die. So it's sent to here and here. Let's see what happens. At location X, it sees this signal. At location Y, it sees this signal. Have you noticed that there's a latency due to the wire delay in the clock signals? Okay, but worse yet, Y needs to do some computation and send the signal back to X. Okay, so X says, this is clock cycle 0. I want to get the result back from Y at maybe here. Okay, I want to see the result from Y at the next rising edge. So X thinks that it has the whole cycle for Y to do computation. But from the viewpoint of Y, I get your instruction at here. And I need to finish my work here so that I will have some time to send my result back to you. Okay, the wire latency is that much coming from clock's generator to Y, plus that much for Y to send the result back to X. This is the clock signal latency. This is the result transmission latency. So actually, Y has only that much time to do computation. That's the so-called clock skew problem. Okay, so when you have a big chip, you need to take clock skew into account. And in conclusion, computer architecture is much more than just instruction set design. And computer architecture skill sets are different. If you want to design computer architecture, you need to know a lot of things 5 quantitative principles of design, quantitative approach to design, solid interfaces that really work. So you need to make things really work, no jokes in designing computers. Okay, everything will have to be exercised, tested in order to make the billion transistor chip or circuit work. And technology tracking and anticipation. If you want to design new computer, suppose that computer will come out in 2 years, then you need to know the technology changes that will occur in these 2 years. Okay? So we learn new skills here, and we can transition our knowledge to research topics and even research results. Computer science at the crossroads from sequential to parallel computing. That's the salvation, but that requires innovation in many fields, including computer architecture. Everything will have to go parallel these days. Okay? No more sequential, especially in the IT field. And we'll skip the RAMP. RAMP is the project name at UC Berkeley at that time. Okay, so let's switch to the next lecture. So lecture 2, introduction. We have seen this for you just then, and we have seen this for you. Have we? Okay, so other fields often borrow ideas from architecture. Yes, we have seen this. And quantitative principles of design include take advantage of parallelism, principle of locality, focus on the common case, and Amdahl's law, we have learned that, and the processor performance equation, we have just learned that. So careful quantitative comparisons. In order to do this, we need to define, quantify, and summarize relative performance. Define, quantify relative cost, dependability, and power. And culture of computer architecture is to anticipate and exploit advances in technology. We need to watch out all the time. Okay? And we need to communicate with the researchers in other fields. And culture of well-defined interfaces that are carefully implemented and thoroughly checked. What we're doing is no joke. We need to make things work. It's not like the algorithm design. The algorithm design can be very idealized. Like if you want to develop a good algorithm for the poker game, how many cards in the poker set? 52? That number is, I don't like it. If that number can be changed to 39, then I can design a better algorithm with much lower complexity. Then let's change that to 39. You think that's a good idea? You think that's a good idea? Rank A journal paper publication. Do you buy that idea? Algorithm people sometimes do that. But in our field, that's not acceptable. Everything will have to be realistic. Okay? Or it will have no value at all. Okay? So, let's do some review. Technology trends, culture of tracking, anticipating, and exploiting advances in technology. And careful quantitative comparisons include this. We have seen this before already. So let's try to understand and track some technologies. Have you heard of Moore's Law? Mr. Gordon Moore said, the die circuit capacity should double in 36 months. But very soon, he changed the number to 24 months. And not long later, the number has been changed again to 18 months. So right now, circuit density on a die, circuit capacity on a die, doubles in every 18 months. That's the so-called Moore's law. So cramming more components onto integrated circuits, stated by Gordon Moore in 1965, number of transistors, cost-effective integrated circuit, double every 18 months. And this law has been valid for over 40 years until today. Okay, even until today. That's the Moore's law. Moore's law has driven many application technologies in the past decades. So let's look at the four most important components in a computer system. Storage, CPU accessible storage, communications within a computer system or among computer systems, and the central processing unit. Let's drill down into four technologies and compare from the 1980 archaic versus 2000 modern designs in terms of performance, in terms of latency, bandwidth. Okay, performance could be latency, how long it takes for you to finish this job, or the bandwidth, how much work you can do in a time unit. Okay, so both are performance matrix, but bandwidth is how many per time unit, and the latency is time. They both take on different units. Okay? Tell me, which one is more important? This is more important, or this is more important to you? Both?
Time.
Can you pick one? Time?
Because if you have big bandwidth and if you still don't have time, you're still going to be slow.
If you're talking on the phone, is bandwidth more important or time more important? Latency more important? Maybe, I don't know. But when I say, hello, how come you don't respond? Later, I hear your response, hello. Are you hesitating? Where are you? Oh, no, I'm not hesitating. I'm at work. How come you pause for so long? Are you really at work? Are you with another girl? No, I'm not with another girl. You lie. You see, latency could cause a lot of misunderstanding. Okay? If I'm talking to you face to face, are you lying? No. Are you with another girl? No. Okay? But if you pause for 10 seconds and then say, no, I'm not with another girl. Of course, very obviously you're lying to me. Okay, so latency could cause a lot of problems. What about bandwidth? If you're running a program, do you care more about bandwidth or latency? If you're watching a movie online, do you care more about latency or bandwidth? Bandwidth? You don't care about latency? Both? Okay, let's see. When I push the button, I want to watch this film. Then it begins to show, okay? Or when I push the button, then I need to wait for 10 seconds. And it begins to play. Do you care about these 10 seconds? Not really. Okay, so sometimes latency is important, sometimes it's not. But if you must choose between the two, maybe I prefer bandwidth more than latency. Okay, now you get the idea of what bandwidth is and what latency is. Let's continue on. Compare for bandwidth versus latency improvements in performance over time. So bandwidth is number of events per unit time, like megabits per second, like mega instructions per second, and whatever. And latency is the elapsed time for a single event, like one-way network delay in microseconds and whatever. So for disk, the old-time disk, CDC RAM 1, has RPM, rounds per minute, of 3600, and the capacity is so many gigabytes, and tracks per inch on the platter is 800, and bits per inch along the track, 1 inch can store so many bits, and number of platters, I have 3 5.25 inch platters. So the bandwidth is this, latency is this, and there's no built-in cache. Okay, don't need to remember all these numbers. Let's compare it with a modern disk. The Seagate newfangled disk has these numbers. The only numbers I want you to pay attention to is the latency has increased by 8 times, yet the bandwidth has increased by much more than 8 times. Why is that? Parallelism. Okay, if you can take advantage of parallelism, then you can increase the bandwidth much more. Should I say parallelism for disk? Maybe not. Okay, so this latency has to do with what? The latency has to do with the seek time. Okay, so the seek time has to do with the RPM. So the RPM increase is like less than 5 times. Okay, so this is about a little over 5 times, because the control time can also be reduced. Yet, this has to do with latency. It also has to do with bandwidth, and this has to do with bandwidth, but does not have to do with seek time. Okay, once you get there, you have this bandwidth. But this does not help the seek time at all. Okay? And this almost has nothing to do with both, but it has to do with capacity. This has to do with capacity. Okay? So if you analyze, this has to do with capacity. If you analyze these numbers, if you understand these numbers, then you will understand why there is only 8 times speed up, but 140 times speed up for the bandwidth. But anyway, if we draw a diagram for the disk, this is a relative latency improvement, only 8 times latency improvement. So latency improvement is only 8 times. Yet the bandwidth improvements is 140 times. So the intersection will be the disk performance improvement from 1983 to 2000. Okay, this may be 2000, 1995, 1990, 1985, something. Okay, so this is the disk performance improvement curve. Next thing we want to look at is memory, memory. The 1980 DRAM has these numbers, and the year 2000 memory has this figure. And again, the latency improvement is only 4 times, as I told you. As the circuit capacity increases and the die size increases, I want to have more memory. Maybe this is 1980, this is 2000. I want to have more memory. And the memory is basically a sequential circuit. So the latency really doesn't improve a lot. What I want more than latency is the capacity of my DRAM chip. So there's only 4 times latency improvement. Yet the bandwidth improvement is 120 times. Okay, so we draw the same curve, we get the memory performance improvement curve. Next is the network. This is the archaic network, Ethernet 802.3. Latency, where's the bandwidth? And this is the modern one. 15 times latency improvement and 1,000 times bandwidth improvement. Okay? So this is the network performance improvement curve. Have you noticed something and begin to wonder why bandwidth improvement always override latency improvement? Can there be exceptions? Should there be exceptions? Next component we want to look at is the CPU. This is a 1982 Intel IA32 CPU and the 2001 Intel Pentium 4 CPU of the same architecture, still IA32 architecture. Okay, latency improvement is 20 times, yet the bandwidth improvement is huge, over 2,000 times. Okay. Plus, it has on-chip memory. So the memory latency is shortened. So this is the processor performance improvement curve. Okay, these are the technological trends in these 4 components. What does it tell you? If you want to design a new system, you should expect these curves to continue in this trend. In other words, you will be given more bandwidth, but the latency will remain about the same. Okay? Does that tell you how to design a new system? Does that give you a good direction? Another thing we need to know is this processor speed increase is far ahead of memory speed increase. We don't care too much about the disk speed. When I say speed, I mean bandwidth or latency. Okay? We don't care too much about the disk speed. Yet we care a lot about the processor and memory speed difference. Why? Because processor talks directly to the memory, but doesn't talk to the disk directly. So that's why in these years we have increased levels of caches from 1 to 3. Nowadays, we always have level 1, level 2, level 3 caches. Okay? So that's another phenomenon that we should pay attention to. And rule of thumb for latency lagging bandwidth. Latency improvement always lags bandwidth improvement. So in the time that bandwidth doubles, latency improves by no more than a factor of 1.2 to 1.4. So this is all like the square root of the bandwidth speed up. And capacity improves faster than bandwidth. So this improves the slowest. This improves faster. This improves the fastest. So stated alternatively, bandwidth improves by more than the square of the improvement in latency. Let's skip this slide. And computer in the news. In 2006, Intel loses market share in own backyard in USA. Intel's share of the US retail PC market fell by 11% points from 64.4% in the fourth quarter of 2004 to 54.3%. So current analysis market share numbers measure US retail sales only, and therefore exclude figures from Dell, which uses its website to sell directly to consumers outside of US. And AMD chips were found in 92.5% of desktop PCs sold in US retail stores during that period. Technical advantages of AMD Atheron versus Intel Pentium 4, as well as we'll see in this course. So the author thinks that the AMD designs are better than the Intel Pentium designs, and that was reflected in the market share at that time. You know the story about Intel and AMD? And a long time back, we also have some other Intel compatible CPU manufacturers like Cyrix, like even local vendors. We have VIA, UMC, also manufactured Intel compatible CPUs. Okay. Because of the huge desktop PC market worldwide. Okay, now let's look into the reasons why latency lags bandwidth. Moore's law, reason number one, Moore's law gives us more circuit and more circuit and more circuit. That doesn't help latency much, but it helps bandwidth a lot. Okay, so faster transistors helps both. More transistors helps bandwidth and even hurts latency. Okay? And then more pins, all these will help bandwidth. Smaller, faster transistor will help latency, but communications latency will limit latency. Okay. Are we done with this? I'll skip all these details. Okay. Reason number 2, distance limits latency. So size of DRAM block limits latency, yet I'm using many high capacity DRAMs, so that can help bandwidth. And speed of light and computers on network were approaching the physical limit of speed. Okay? And there are many computers on network, so latency cannot be increased much, but bandwidth can. Reason number 3, bandwidth easier to sell. So even if just marketing, customers now trend not very well trained. We're still trained by only the buzzword clock rate. We don't understand much other than the clock rate. And since bandwidth sells, more resource thrown at bandwidth, which further tips the balance, makes it more unbalanced. Reason number 4, whenever you improve latency, that will help bandwidth. But when you improve bandwidth, that may not help latency. Worse yet, that may even hurt your latency figure. Okay, so spinning disk faster improves both bandwidth and rotational latency. But lower DRAM latency makes more access per second, so we get higher bandwidth. So this latency improvement will help bandwidth. Higher linear density helps this bandwidth, but not disk latency. Okay, so this is reason number 4. Number 5, do we have 6 reasons? Okay, here. Bandwidth hurts latency. With queues, buffers, we can increase the bandwidth. Tell me what a buffer is. When do we need to use a buffer? I have a producer which generates some results to be used by my consumer. If the producer produces the results at a known speed, and the consumer also consumes the results at that speed, what should I do? Simply send the result directly to the consumer. Use it. Okay? However, if my producer can produce results faster than the consumer, what should I do? Use a buffer? Use a buffer? Say that again. Use a buffer? Okay, so this is faster. This is slower. And then you say, put it in the buffer. And let the consumer pick the results up out from the buffer. Is that right? Any objection? No objection? This is a lousy design. Tell me why it's lousy. Eventually, that buffer will explode. Never, never, never do that. Okay? So the buffer is used when the speed of the producer is not stable, or the speed of the consumer is not stable, or both. But in the long run, they should have the same speed. Otherwise, the buffer is useless. Remember that. Most students just say, if the speeds are different, then I use a buffer. That's a wrong concept. That design will never work. Okay? So that's when we should use a buffer. So if the speeds of the producer or the consumer or both are not stable, then queues can help bandwidth. But whenever there's a queue, results go into the buffer, and then out of the buffer will increase latency a lot. So using a queue will hurt latency. And adding chips to within a memory module increases bandwidth, but higher fan out on address lines may increase latency is another example why that hurts latency. Number 6, operating system overhead hurts latency more than bandwidth. So with the help of operating system, usually this computer system can do more things, helping the bandwidth. But the latency of each task may be much increased. Okay, that's another reason why operating system will hurt latency but help bandwidth. Long messages amortize overhead. Share the overhead. So overhead, bigger part of short messages. For short messages, this overhead is more obvious. This overhead means latency. It's more obvious. So for long message, maybe you don't see that, but for shorter messages, you can very obviously see the latency increase. Okay, let's continue. Summary of technology trends. For disk length, memory, and microprocessor bandwidth improves by square of latency improvement. And lag probably even larger in real systems as bandwidth gets multiplied by replicated components. So in a real system, you may use 2 CPUs, you may use use a disk array and whatever, okay? So multiple processors in the cluster or even in the chip. Multiple disks in the disk array and multiple memory modules in the large memory and simultaneous communication in switched LAN. And hardware and software developers should innovate assuming latency lacks bandwidth. So if you're designing individual components, you should learn from the past that bandwidth is easier to improve. If you're to design a complete system, you should remember that bandwidth will be increased much faster than the latency, and design your system in that direction. If everything improves at the same rate, then nothing really changes. If everything remains at the same improvement rate, then the system design would be no challenging at all. Okay, you just use the same system design from your old conventional wisdom. When rates vary, then the new system design will require real innovation. Okay, next topic will be the power. Power, there are 2 different matrices. One is energy and one is power, wattage. Okay, so when I say energy, I mean how many joules. How does number of joules concern you? Why do you care about number of joules? Why? Because it has to do with your electricity bill. Okay, that's how much you need to pay. And also because it has to do with your battery capacity. That determines how long your battery can last. Okay, what about wattage? Why should we care about wattage?
Cooling system.
Oh, right. If your system burns a lot of power in fixed amount of time, then your system will heat up. And if it gets too hot, then you need to cool it down, putting in extra energy, extra devices like a cooling fan. Here we talk about power. For CMOS chips, traditional dominant energy consumption has been in switching transistors called dynamic power. So in CMOS, what is the signal? What is the signal in CMOS circuit? Do you know? Voltage, amperage, or the intensity of light? Of course, it's voltage. Okay, in CMOS, the signal is the voltage on the gate of a transistor. And this voltage comes from the charge on the gate. So V is over to Q over capacitance of the gate. Okay, so the real signal comes from the charge. If you want to turn this transistor on, you put that much charge on the gate. Later, if you want to turn it off, you drain the charge. So you need to charge it up, discharge it. That's how power gets consumed, energy gets consumed. So you want to charge it up and discharge it, and you want to do this several times in a time unit, then we call that dynamic power. It occurs dynamically. It occurs all the time. So the dynamic power can be represented by this equation. 1/2 times capacitive load times voltage square of voltage and times frequency switched. For mobile devices, energy better metric is how much energy you can store in your battery. And the energy equation is capacitive load times voltage square. So for a fixed task, you have something to do. Then what you care about is how to spend the least power, or in other words, how many joules to accomplish that task. However, if you care about the heat dissipation, then you care about how many watts are burned in a second. I should say how many joules are burnt in a second, which is watt. So slowing clock rate can lower your wattage but not energy. And capacitive load is a function of number of transistors connected to output and technology, which determines capacitance of wires and transistors. And dropping voltage helps both. By lowering the voltage, it can help to reduce power or energy the most, because this is a quadratic term in the equations. That's why we're reducing the supply voltage from 5 volt to even below 1 volt these days, especially in mobile devices. Okay? And to save energy and dynamic power, most CPUs now turn off clock of inactive modules. So this is a CPU. Within the CPU, we have fetcher, decoder, maybe register file, ALU, maybe several of those, and interface, whatever. For every instruction, maybe we don't need to use some of these. Then what do? We simply don't let these components to switch. So one way we can do is we have a clock generator, right? We send clock to here and here and here and everywhere for whichever component that we're not using. Maybe we gate the clock. Don't let clock to go into that component. That's the so-called clock gating. Or we have power net to all the components. We may even gate the clock to those components that we don't need. Okay, so that's called clock gating or voltage gating to save power. That's one of the reasons why we want to design the circuit in a modularized fashion, so that it's easier for us to gate the clock or gate the voltage supply. So have we defined what the power is? Yes, we have. Could be watts or joules. Do we know how to quantify them? Yes, we do. This is the power equation, and this is the energy equation. And if you really want to quantify them, then for every output signal, you have one power equation and one energy equation. For the whole circuit, you may have millions, billions, of these equations or these numbers for you to sum up to obtain the whole chip's power or energy figures. Okay, a very complicated task. So usually, if we have billions of transistors, billions of gates, what do? Then we simply assume that half of them are switched on, half of them are switched off, and multiply this by number of outputs, and then multiply that by 1/2, meaning half of them are wasting power, but the other half are sitting silently. Okay? That's how we estimate power in a big circuit. So suppose 15% reduction in voltage results in 15% reduction in frequency. If you lower the supply voltage, then it will take longer for you to charge the gate up to that voltage. So whenever you lower the voltage, you need to lower the frequency. I mean, if you lower VDD supply voltage, then you need to lower frequency accordingly. Okay? So have you heard of a new term called voltage and frequency scaling? Okay? In a circuit, maybe I don't do gating. But I change the voltage supplied to each module in my circuit. Okay? So if I change the voltage supplied to each individual module, I need to change the frequency accordingly. In the meantime, that's the so-called voltage and the frequency scaling. And this is often done dynamically. So that technique is called dynamic voltage and frequency scaling, DVFS. You should have heard of this term very often these days. Most chips have that capability built in. So if we do this, what's the impact on dynamic power? In this example, we list the equation and plug in the numbers and get the result of only 60% of the old power is consumed. What about the energy? Does energy remain the same, or energy will change? If it's 60%, no, it's, let me see, 85% of the original speed, right? So you would take 120% of the original time to finish the task. So we get some energy saving, but not that much. Still, we save some energy. Okay, in reality, that may not be the case. If we reduce the voltage to the lights by 20%, how much light do we get? Usually we don't get 80% of the light. Maybe we get only 60% of the light. Okay, 20% supply voltage reduction results in 40% illumination reduction. Okay, so if you reduce this by 15%, usually the frequency reduction would be much higher than 15% only. Could be 30%, could be something even worse. Okay, so in the end, your energy consumed may get even more. Got the idea? If you want to reduce power, usually you spend more energy. If you want to reduce energy, maybe you want to finish the task in a much shorter time. In other words, increase power consumption. Okay? Okay, because leakage current flows even when the transistor is off. Do you know that current will leak? How does it leak? We talk about green computing all the time these days. And green computing means low power computing. Low power computing, then we need to know where does the power go. There are three components of the power. One is dynamic. This is used in computation, in communication. These are the useful part of the power. The other is static. Static means whatever that current will flow. Okay? And the final component is leakage. Leakage power is due to this. I have a transistor. This is the gate. This is the source. This is the drain. This is a MOS circuit. This is a substrate. Oh, okay. Leakage power means when we reduce the dimension of our transistor. We reduce the dimension, then electrons on the gate can tunnel through to the substrate. Similarly, electrons can also tunnel through from the source and drain to the substrate. Also, in the meantime, even if the gate is off, there can be thermally generated current flowing from source to drain. I should say from drain to source, because this is usually of the higher voltage level. Okay, so these are the sources of leakage current. As the IC technology gets more and more advanced, the feature size of our IC circuit becomes nanometers, right? 45 nano, 22 nano, right? So the gate insulation layer gets thinner and thinner, so the tunneling of electrons becomes very severe. Tell me, for 100% power consumed, how much is the leakage power? How much is the leakage power? For 100% of power consumed, how much is the leakage? Give me a guess. 20? You say 20? Over 70. Over 70 of the power is leaked. Leaked away. Did nothing, just wasted. So what can we do? We want to make the insulator layer thicker. So we put gate here and use a much thicker insulator layer such that the electrons cannot tunnel through the gate insulator layer. Okay? But by doing that, the capacitance becomes much smaller. In other words, it's much more difficult to use the gate to control the transistor, right? So what do? We use high K material as the insulator. Have you heard of high K? Copper? No? Yes? You should understand these. By using high K, this layer is no more SiO2. So we don't need to use polysilicon for the gate. We can use copper instead. Okay, so once we use copper, since copper is a much better conductor, we can raise the clock rate to over 1 giga. The first 1 giga microprocessor released in 1996 used the copper process. Okay. If this is SiO2, then I need to use polysilicon for the gate. Otherwise, when I operate the transistor, if this is not Si-based material, it will crack, will break away. Okay? But if I use different material, then I have the freedom to use other material for the gate. Okay, so in 2006, goal for leakage is 25% of total power consumption. High performance design at 40, and that's the goal. That's something where we were unable to achieve. Okay, the reality was 70% or even higher. Okay, so now you understand what leakage is. Because leakage current flows even when a transistor is off. Now static power is important too. For CMOS, there's no real static power. So sometimes people call this leakage static. In CMOS only. In NMOS, these two terms mean something very different. Okay. Okay, so power static is equal to current static times voltage, and leakage current increases in processors with smaller transistor size. As the transistor feature size decreases, the leakage current increases. So increasing the number of transistors increases power, even if they're turned off. Not only because we have thinner and thinner gate insulator layer, but also because we have more and more transistors. So the leakage current increases like crazy. And very low power systems, even gate voltage to inactive modules to control loss due to leakage. I have mentioned this. Don't supply any voltage to it. So there will be no leakage at all. Otherwise, more or less, you will have leakage. Dependability. Is dependability important? For instance, we have two classmates in the class. This guy is super smart. He knows everything. He knows about everything. But his performance is not very steady. Sometimes he can show his capability. Sometimes he just makes silly mistakes. This guy is okay, a mediocre student, but his performance is very steady. Always can do his job right, although not very well. Okay, if you are the boss of a company, which one will you like to hire? This guy, because he's so smart, so you don't care even if he can mess up some big cases sometimes, or this guy. So you see how dependence or dependability, how important it is. Okay. So let's define and quantify dependability. How to decide when a system is operating properly. If a system is operating properly, then we say it's up. If it's not, then we say it's down. So infrastructure providers now offer service level agreement to guarantee that their networking or power service would be dependable. Okay, so what do you mean by dependable? I need a number to measure that. What will the number be? Let's go on. Systems alternate between two states of service with respect to a service level agreement. So one is service accomplishment and the other is service interruption. Service accomplishment says where the service is delivered as specified in this agreement and where the delivered service is different from what's stated in the agreement. And we call this a failure. So a failure means if the system transitions from this level to that level. And restoration means the transition from this level back to that level. And the dependability or reliability equation says measure of continuous service accomplishment or time to failure, which can be broken into two matrices. One is mean time to failure, the other is failures in time. Mean time to failure says from one failure to another failure, how much time would that take? In millions of hours. Okay? And failures in time, I'm sorry, in seconds. And failures in time is equal to 1 over mean time to failure, which says the rate of failures in millions of hours. Oh, I'm sorry, billions of hours of operation. Well, that doesn't matter. That depends on the common agreement of people in this field. So another time we need to know is mean time to repair. How much time do we need to repair the system? Then mean time between failures, MTBF, is equal to mean time to failure. It can stay up for that long, plus once it fails, how much time it would take for you to bring it up again. So the module availability measures service as alternate between the two states of accomplishment and interruption. And its equation is mean time to failure over mean time to failure plus mean time to repair. Given 100 hours, maybe 95 hours is operating, and then once it fails, you need to spend 5 hours to repair it. So the module availability will be 90% of the time. That's a module availability, very simple equation. If modules have exponentially distributed lifetimes, and the age of module does not affect probability of failure, then overall failure rate is the sum of failure rates of the modules. So if you have a system consisting of many modules, then your failure rate will be the sum of the failure rate of the modules. So how do we calculate FIT and MTTF for 10 disks? If every disk has 1 million hour mean time to failure, and we have 10 disks, plus one disk controller, which has 0.5 million hour mean time to failure, and one power supply, which has 0.2 million hour mean time to failure, then the failure rate, okay, so the failure rate, in other words, the failures in time, is equal to 10 times 1 over 1 million plus 1 over half a million plus 1 over 0.2 million. And the result will be 17,000 failures in time. Okay? And mean time to failure will be 10 to the 9th hours, in other words, 1 giga-hours over your failure rate. So mean time to failure will be 59,000 hours. Okay, 一场 not on the screen, but in your lecture notes. Okay. So if this system breaks, which component is the most likely failed component, do you think? Power supply. Okay. So no matter how strong your disks are, for a system, you have 10 disks and 1 control unit and 1 power supply. So it's just like a chain. A chain, when you pull it hard, it always breaks at the weakest link. Okay. No matter how good your disks are, how reliable your controller is, as long as there's a weak link in the system, then your reliability or mean time to failure is determined by the weakest link of the whole system. Okay, next, we define performance. As I told you, performance could be in latency or in bandwidth. Here, let's assume performance is in units of things per second. So the figure is bigger is better. And however, if we're primarily concerned with response time, what is response time? Response time is latency. Okay? If we are concerned more about latency, then performance is equal to the reciprocal of execution time. And when we say this machine is n times faster than that machine, then x is 1 time faster than y means they're of the same speed. Okay, different from what we're used to describe it. So n means the performance ratio of the two machines. So if they have this equal performance, then this figure will be 1. 1 time faster means they're of the same speed. So you want to buy a notebook. And before you make the purchase decision, you want to know how fast it is. How do you measure the speed of this thing? First, peak speed. Do you think peak speed is meaningful? Yeah, to some extent. But that's far from being realistic. So another way to measure speed is to use benchmark suites. A benchmark suite contain a lot of commonly used programs, typically more than 10. Okay? So what are the typically used programs? For you, what is your typically used program suite? Well, it's really difficult for you to answer this question. So there's a company called SPEC. Standing for System Performance Evaluation Cooperated, to design different benchmark suites for users to use. One suite is the SPEC CPU used to measure the performance of general purpose CPUs. What do I mean by general purpose? Means it can do everything, but you cannot do anything too well. Okay? That's the so-called general purpose. So for the SPEC CPU benchmark suite, in year 2000, we have 12 integer programs and 14 floating point programs in this suite. And we changed the way we use computers, right? So the benchmark suite will need to be updated in every 3 years or so. So we expect to have a new CPU benchmark suite in 2003, and in fact, the next suite came out in 2006. This first suite came out in 89, and then 92, and then 95, and then 2000, and then 2006. Today, we're using the 2006 benchmark suite to evaluate general purpose computer systems. Okay, let's begin from the beginning. Usually, performance measurement relies on benchmarks versus real workloads. And to increase predictability, collections of benchmark applications called benchmark suites are popular. And these are some typical benchmark suites. First one is Spec CPU, popular desktop benchmark suite for CPU evaluation only, not even for the whole system. It doesn't evaluate much about the I/O and memory. Okay, so it's split between integer and floating point programs, and Spec CPU 2006 to be announced spring 2006. It come out already, and Spec SFS for the NFS file server and Spec Web for the web server evaluations are added as server benchmarks, and you have heard of like this transaction processing console has their own benchmark suite, and Spec also has Spec Web, Spec Java, Spec whatever is needed and can make them profit. Okay? Okay, so we have a collection of test programs. Benchmarks are those test programs. If on machine X, speed of this is 1, always normalized to 1, 1, 1, 1, 1. That's how fast this machine can run these benchmarks. On machine Y, Spec relative to the speed of the first program relative to X is 0.5. Relative to this machine is 3. Relative to this machine is 0.1, etc. You see, sometimes this machine is faster, sometimes this machine is slower. How do we summarize these numbers and come out with only one single number representing the performance of Y? How should we do that? Add them up, divided by number of benchmarks? Why not? Why do you say no? Because some programs are huge, some programs are tiny. So how should we summarize performance? It's easy if we have only one single program, but it's difficult if we have different applications and need to use a set of programs. How can we do that? We can do arithmetic average of execution time of all programs. Okay? But when we do that, we need to add in another flavor, which is the weighting of the program. For instance, if this program is huge, then maybe we multiply this speed, relative speed, by a larger coefficient. If this is tiny, then maybe we multiply that by less than 1 coefficient and so on, and then add them together, and then divide them by the number of benchmarks. So we could add a weight to each program, but how to pick the weight? Different people will have different opinions. So we have another way to do that. Spec ratio normalize execution times to reference computer, yielding a ratio proportional to performance. we pick one computer which is commonly acceptable to other companies, which is VAX 11780. I'm sorry, 780, and calculate the relative performance of the other computers to this VAX 11780, and use these numbers, perhaps adding a weighting factor, to summarize the execution time. Summarize the execution time. So for the time, we can do this. Can take the arithmetic average. What if it is the speed? If we use time to do the calculation, or if we use the speed calculation, will the equation be the same? Yes or no? If y fails to run this program, then the time it needs is infinity. That's bad, as you can see. However, the speed is 0. That's not too bad. I can handle a 0, but I cannot take it if it's infinity. So if we want to summarize performance in terms of time, we need one kind of equation. To summarize the performance in terms of speed, we need another kind of equation. Okay. Now you know this. We'll talk about this later. So if program spec ratio on computer A is 1.25 times bigger than computer B, then this will be the spec ratio of A, spec ratio of B. And remember, we have a reference machine. But this execution time of the reference machine eventually cancels each out. Okay, so they will cancel each other out. So finally we found out which reference we pick does not matter at all. That's why we think this summarized method is fair. Okay, whichever reference machine you pick, the result remains the same. So note that when comparing two computers as a ratio, execution times on the reference computer drop out, so choice of reference computer is irrelevant. Okay, so when we compare the computers in terms of speed, as you already understand, speed is different from time. If the metric you use is speed, then the equation you should use is geometric mean, which is like this when comparing speed of computers. Okay, on the foil, it doesn't explicitly tell you that, but you should understand that. Okay, so when you are comparing time, use arithmetic mean. When you are comparing speed, use geometric mean. For more detail, you need to read the textbook. So I'll skip the following 1-2 slides and let you read them through. Okay, here we only compare two different machines, geometric mean and multiplicative standard deviation of spec floating point 2000 for Itanium 2. We're comparing the floating point part of the two CPUs. You know Itanium 2? Itanium 2 uses the IA64 architecture. You know IA32? This is the x86 architecture. But later on in 1990-something, people begin to think, while 32 bits is not enough. We need more bits. So next thing to go to is 64 bits, right? Tell me, what's the difference between 32 bits and 64 bits? Don't tell me the difference is 32 bits. Are we trying to represent larger numbers, or what's our intention to use more bits?
Memory addressing.
What?
Memory addressing.
Right, we're dealing with larger files. We need more locations to store the information. So 32, 64 indicates larger address space. Doesn't mean we need more bits to represent numbers. Okay? Okay, so Itanium 2 is a 64-bit machine. Also, AMD Atheron can run in 64-bit mode or 32-bit mode. Okay, so for different floating point benchmarks, this machine has these performance. This is the mean, and this is the standard deviation. And sometimes its performance is much better. Sometimes the performance is worse. See, these 2 points fall outside of the range of standard deviation. Okay, and for the Atheron, the standard deviation is much smaller. Okay, so for that Itanium 2, we have this kind of performance. The average is around 3,000. And standard deviation is, oh, okay, numbers are here, 1.98. And for the Atheron, it's a more predictable machine, although the performance is a little lower. So do you think that's a better design, or this is a better design? In terms of design, this is a better design. In terms of performance, it's sometimes hard to tell. Okay, but this machine is more predictable. So these are the comments. So falling within one standard deviation, 10 out of 14 benchmarks do, or 11 or 14 benchmarks for the Atheron. Okay, in conclusion of lecture 2, tracking and extrapolating is like forecasting. Okay, tracking the past and forecasting the future of technology changes is part of architects' daily responsibility. And we should expect bandwidth to improve much faster than latency, because we have seen these facts and we understand why these are so. And then we have quantified the dynamic and static power and understand how to control our wattage or joule consumption. And we have quantified the dependability of a computer system containing many modules. And we have quantified and summarized performance of machines using benchmark suites. And you don't need to worry about how the benchmark suites are designed. Just pick the right ones for you. Sometimes, in some research areas, there have not been any good, commonly acceptable benchmark suites yet. However, there are some commonly used programs to do evaluation. Remember in image processing, there's a girl wearing a hat. Remember that figure? You see that picture all the time. Okay. So that single picture has been used in many research works. And you can also read Appendix A of our textbook. Lecture 3, Performance plus Pipeline Review. Okay, we have seen, we haven't. We haven't. So we'll do a little bit of review and quantify and summarize performance and fallacy and pitfalls. And then we study MIPS, pipelining, structural and data hazards. And another is control hazard. I don't know where it is. Okay, this has to do with the control hazard. First, at the end of every chapter in the textbook, the author provides some fallacies and pitfalls at the end of every chapter. And fallacy means commonly held misconception. Fallacies are big mistakes. Okay? And pitfall is easily made mistakes. What's understood can be right, but it can also be wrong sometimes. For things like that, we call it a pitfall, like a trap. Okay? And something's absolutely wrong, then we call it a fallacy. Okay? So, first fallacy in, I don't know which chapter in the textbook, says benchmarks remain valid indefinitely. Okay, so we have a 1989 spec CPU benchmark suite. Do we need to have a new benchmark as time goes? Why is that? What I really want to know is why. Because the way we use computers change all the time. Long time back, we used it to run Fortran. Anyway, to run programs. How many of you run programs on the notebook? Almost none. Okay, almost none. Long time back, we used notebook to edit Word files. Okay, at that time, not many people can send or receive emails. Not many people have email accounts. Nowadays, how many email accounts do you have? You don't know. You don't even know how many email accounts you have right now. Okay? So that's for one reason. The other reason is people tend to cheat. So if this is a benchmark, perhaps I compile it using different optimization levels because I want to win the game. Okay? Perhaps I use different data set because you didn't specify that in your benchmark specification. Or even worse, whenever I see the maybe special keyword or the name of the benchmark, I don't even calculate because I know what this is. I directly give you the result. Okay, so people did all kinds of tricks to cheat. That's also one reason why we need to change benchmarks and even change the rule of the game, how you should compile it. And this is a standard data input file. You have to use it. Okay? So once a benchmark becomes popular, tremendous pressure to improve performance by targeted optimizations or by aggressive interpretation of the rules for running the benchmarks. So you can do all kinds of tricks to just run these benchmark programs well and don't care about anything else. Okay? So will that lead to good products? Maybe not. Okay, so all these kind of tricks are called benchmarksmanship. So from 1989 to the year 2000, 70 benchmarks from the 5 spec released. 70% were dropped from the next release since no longer useful. Every time the benchmark suite has 70% of the original programs dropped. And this is the remained 30% plus maybe some new ones. Okay, every generation of new spec CPU or whatever. Okay. Next is a pitfall, a single point of failure. So rule of thumb for fault-tolerant systems, make sure that every component was redundant so that no single component failure could bring down the whole system. Like in our disk system example, power supply is the weakest point of the link, weakest link of the chain. Okay? So this is something we should pay attention to. Next, rated mean time to failure of disk is so many hours or 140 years. So disks practically never fail. You never need to replace your disk. Is that true? How often do you replace your hard disk in the computer? Every 2 to 3 years. But according to the manufacturer, it will not fail in 140 years. What's the difference? The operating environment, the humidity, dirt, vibration. Okay? So this figure is obtained in a controlled environment. Plus, they don't have 140 years to do the test. So instead, they use thousands of disks. Let them run simultaneously. And after a fixed period of time, see how many of them failed to calculate the mean time to failure of a single disk. And of course, in that environment, temperature is well controlled, humidity, and whatever is well controlled. But disk lifetime is 5 years or even shorter, so replace a disk every 5 years or expect trouble. Expect delay in pursuing your degree. On average, 28 replacement won't fail. A better unit is percent that fail. And fail over lifetime, you've had 1,000 disks for 5 years, then the fail over lifetime is how much? Okay, but this is under pristine conditions. Real world, 3% to 6% of SCSI. SCSI stands for what? Anybody know? Small computer serial interface? I don't know, but you need to know, because it does have meaning in it. Okay, so don't just call it SCSI, don't just call it, what else? What else? We have just encountered DVFS, right? And what else? A lot of these. Okay, a typical risk ISA. I think time is up. So we'll talk about risk. And I want you to get a true understanding of the risk as well as CISC design. So tell me if RISC is a better design or if CISC is a better design. If you get it right, then you can be dismissed. CISC and RISC, which one is the better design? RISC? What?
RISC is simpler.
My question is not which one is simpler. Which one is the better design? If you think RISC is a better design, raise your hands. Okay, if you think CISC is the better design, then raise your hands. And what's the matter with you two guys? Right, okay, you two can go. The others stay. Okay, it all depends. You know what's the shortcoming of risk? Tell me what's the shortcoming? I mean, shortcoming. Shortcoming is every instruction will have to go through the same life cycle, whether you need any stage or not. Okay, wasting a lot of power. Who says it's a good design? A lot of things can be improved. Okay, so they're just different designs. They're just designs suitable for some particular technological background. Okay, none is more superior than the others. Okay, keep that in mind. See you next week.